Hi everyone. Okay, so I just recorded the early hominin genera, and now moving right into the next one. Australopithecus and Paranthropus. So those, you will learn how to pronounce these, trust me. Those are also more genera from the human lineage. So if you're looking at the title slide on this PowerPoint, you will see it has "I Love Lucy" and then it has a skull. This is because one of the very famous finds, hominin finds, fossil finds in our lineage, was given the nickname Lucy, and that's one of the Australopithecines. So we'll talk about her in a minute, but in case you were wondering. So moving on to the first slide, if my PowerPoint wants to work. There we go. So you'll see right away we've got some naming things I want to talk about. So we back up a little bit in time. Initially, when paleoanthropologists first started finding these fossils, because remember, there was a time when there were no fossils, whether it's our lineage or other animals, right? There was a time, a long time ago, when, scientists, people had some ideas about what they would find in our lineage. And actually, this is something we're going to talk about more, too. A lot of these incorrect preconceived notions that they had. So imagine, but I mean, so you have to give a little grace, because if you don't know, right, you're just making a guess, you have nothing to go off of. Then later we start finding stuff, and then you're like, well, you still weren't believing it, even though you were seeing it. But okay, anyway, before I get too ahead of myself. So basically, these individuals, scientists, thought, what are the things that are kind of separate humans from other types of animals? And then those are the features we're probably going to see in our lineage. And so for many of them, they thought, well, it's how smart we are, right? It's our big brains. Big brains, something we have that we don't really see to the same degree as other animals, right? They were right and wrong about a lot of that. But this preconceived notion that big brains is kind of like the hallmark of our lineage, and that would be what we see for like our entire lineage would be big brains. Now, that's part of it, but they thought we're going to see big brains really early, because that's clearly the thing that separates us as, humans, right? What they didn't know is that we see big brains in our lineage, but we see them much later, like the last third of our lineage. They're getting a little bit bigger here and there at the beginning, but not anything near like a big brain they thought they would find. We don't have that until much, much later in our lineage. They also thought like the bodies of our ancestors would be kind of more like ape-like or chimp-like bodies, but just with big heads, right? So they thought they would see, like this ape-like, maybe even quadruped body with just a really big head, very intelligent, right? Well, now we know, based on all the fossils that we've discovered along, the decades, if not centuries, since this, that they got it kind of the opposite, right? We're fully bipedal, modern height, and then we get the bigger brains, right? So it was opposite of what they thought. So as you can imagine, some of these early finds, from different scientists, we're going to talk about some of these. Some of them are really famous for this, that they were completely disregarded by their fellow, whatever, scientists, naturalists, paleoanthropologists, whatever the term was at the time, because it didn't fit these preconceived notions, right? And one of the other preconceived notions was that they thought, well, of course, like Europeans are the better humans. Incorrectly, of course. And so they thought they were going to find all of the human lineage stuff in Europe. Now, some of it happens in Europe, but the later stuff, right? The majority of the human lineage occurs in Africa. And so when some of these early finds were discovered in Africa, a lot of people in the scientific community were like, oh, can't be possible, right? They were totally wrong. So we'll get into some of those finds later, but I just want to kind of back up with what I'm starting out with this one, that sometimes, you don't have anything to go off of. You're naming things as you're discovering them. And then, of course, as you discover new things, you realize we actually have different categories, or maybe similar categories. And maybe we need to reconsider the names because of X, Y, Z. And so that's exactly what happened in this scenario. So imagine there's a time where these fossils are being discovered, and they're kind of in the same location, dating to similar times, and there's enough of a difference to say, oh, here's maybe one species and here's another. And so we start to give them the genus name Australopithecus. And so we call them the Australopithecines, right? And this is fine. But then as more and more, like I said, in the same location, sort of, like all in Africa, some in like South Africa, some in like East Africa, dating to around the same time and stuff, now we're realizing with all of these fossils that are being discovered, it seems as if there's actually kind of two groupings kind of emerging from this. One group we have named the graciles, which basically is a reference to like their bone structure. It's not their bodies, right? Not the soft tissue. Their bone structure. Basically, the bones tend to be a little more smaller, maybe smoother in muscle attachment areas, maybe certain areas that protrude more in the other group aren't as protruding, in the gracile group, because in the other group is called the robust group. And so they have, areas of their skull and stuff where their prominences are really large, or things are wider, or things are bigger. And so it seems as if, there's two kind of groupings emerging. My dog's doing something weird over there. I'm going to check on her in a second. I don't know. Waffle, you okay? Waffle. Hold on. What is this? What is this? What is this? Did you pee pee? Oh, okay, hold on. Yeah. Okay, everything's fine. We got a teenager on our hands, Waffle 17, and she's just recently has had some bladder issues. We just started her on some medication, and we have some like pee pads, like on the couch, kind of where she lays, and we have diapers. Well, all of her, because we got the reusable ones, just for the sake of the earth. And so they're all like being washed right now. And so we're like, oh, she'll be fine on the couch for a couple of hours. And she was doing something weird with her leg. I'm like, oh, she's peeing. She's just peeing on the couch. Luckily, we have a little blanket and the pee pads underneath, so I put her outside and I took the other stuff off. You guys don't care about this, but okay. I'm not starting the recording over though. Okay. So that's fine. So going back to, like I was saying about the Australopithecines and the Paranthropines. So as these two groups are kind of emerging, what we were still calling the whole group the Australopithecines, but we were calling one group the graciles and one group the robusts. And so we'd say, oh, the gracile Australopithecines or the robust Australopithecines. Well, then, of course, long story short, basically, we get more fossils. We're starting to rethink these categories, understanding maybe some branching events actually were happening, cladogenesis, in terms of like, how the lineage actually was going, and realizing we can actually give this robust group an entire, like, its own genus designation. It's different enough. We talked about before, like, how are we conceptualizing a species? Like, what is a species and how do we determine one species from another? It's the same for all of these groupings, or, kingdom, phylum, class, or, all of that. So genus too, like, what is a genus? How are we defining a genus? When we're actually looking at individual species, how are we saying one is in one genus and one is in another? And so this is all something that's going on in the scientific community. And so then, of course, we realize we actually have two different genera. Yeah, they're around the same time, same locations, probably interacted with each other, like, to some degree a little bit. But they're clearly different enough to where we can say they're actually two different, genera. And so if you are looking at an older textbook, or if you have an older instructor, they might still refer to the old terms and call them like, oh, just all of them the Australopithecines, or say, oh, the robust Australopithecines, the gracile Australopithecines. Some still do that. Like, contextually, those of us in the field, we understand exactly what they're saying. It's like not a big deal, right? But I would say the majority of like newer scientists, younger ones, well, I'm not young, but you know what I mean, we tend to refer to it as the Paranthropines, or like the Paranthropus as the genus, right? So, but if you're like, oh, they're talking about the robust Australopithecines. Oh, when I was in class, we talked about that group actually being called, Paranthropus. Just know that that's kind of you're seeing like science in action, changing with new evidence. We're kind of in the process of this is changing a little bit here and there. And so just I know there's a lot of long names that you're having to learn, and it makes it even more confusing when the consensus on them in like a textbook or one instructor to another instructor isn't always 100%, but that's just, kind of part of how it is. Okay, so moving on to the next slide, you will see that I'll show you these along the way, kind of that visual timeline. So you're seeing we talked about the early genera on the previous video. Now we are talking about that middle group, the Australopithecines, the Australopithecus genus and the genus Paranthropus. We're going to talk about those. And you'll see also in that timeline there's a group later that we're going to talk about. Well, there's an area for a group we're going to talk about later. So you'll see here some of the gracile features. Like I mentioned, when we talk about gracile, typically that means, short, like, I'm sorry, not shorter. Well, it can be, but that's not what we mean here. But like smaller, smoother. It really depends on the context of how you're using that term. So we're using it in a reference to like the skeletal features because, that's what we have. So these two groups, the gracile group and the robust group, or the Australopithecines, versus, Paranthropus, from the neck down, essentially the same. They're the same height, basically the same brain size. Is not like one group smarter than the other, right? Same brain size. The Paranthropus group, they probably had a little bit longer of a gut system, so maybe they had a little bit more of a tummy, Like when you see a modern gorilla, they have kind of a belly. That's not because they're fat. That's because the gorillas are folivores, right? We talked about, folivore, frugivore, insectivore, all of that. So folivores, they're eating maybe not the best part of the plant, maybe the fresh, ripe fruit part, but they're eating leaves and stems and bark and stuff like that. You can still get nutrients from that. It just takes your body a bit longer. And so typically the gut system, like the actual intestines, are longer, and so it just makes it look like there's a bit of a belly. So for the gracile group versus the robust group, in terms of what we're talking about right now, many paleoanthropologists say, well, even though they're like the same height, same brain size, maybe the gut system of the Paranthropus group was maybe a little longer, so maybe they had a little bit more of a belly, but like minimal differences, right? It's really from the neck down, imagine they're the same height, same brain size too. It's really what's going on in like the face, the jaw, the head. That is where we see the features that we would say, gracile versus robust, right? So you can see some of these things here. So one, you can see the brain size average. We're seeing a little bit of a jump. If you recall from the early genera, brain sizes were still around like 400. So now we're seeing a bit of a range, maybe even into like the 500 range. So brains are getting a little bit bigger at this point. We don't see it, like I said, a big jump until much later. We still have, I have large there. I should really put like medium to large, larger maybe, larger than what we have now. But the molars and the premolars, the incisors and canines, you can see basically all of the teeth for the gracile group. All of their teeth are kind of a bit bigger than we have now. Now, of course, there's no goal towards having small teeth. We just see that happening in our lineage. So when we compare our teeth to what we saw, a few million years ago, like obviously, their teeth in general, all of them were all a bit bigger than what we have now, right? So that's kind of an interesting trend. So I have gracile skull features. So just imagine areas of muscle attachment are a bit smaller than what we see with the robust group. You see here it says moderate muscle complex. Whenever you have on the bone an area that's rough or rugged looking, or a part that's arching over or protruding out, typically that is an area where a muscle is coming and attaching to that area. So if the muscle is bigger, that area will be, longer, larger, protrude more, be more rough and rugged looking than if the muscle is smaller, right? A little bit of variation in that. So what we see is on the graciles, because their muscle complex is a bit, more medium, those features aren't as large as what we see with the robust group, where those muscles are massive. So of course the areas of muscle attachment will be larger. The areas to accommodate those large muscles will also be bigger, wider, right? So we're going to have a couple slides in a second kind of showing that side by side. But you'll see here underlined and in bold, it says the reasons for the difference between the gracile group and the robust group, or the Australopithecus and Paranthropus, is diet. That is the main difference. It is what they are eating. What they're eating is going to massively change what their teeth look like, what their mandibles look like, what the muscles they use for mastication or chewing are going to look like. It's all because of their diet. Basically, the gracile group, imagine they're eating kind of similar to a modern chimp, like soft, ripe fruit, probably the occasional insect. Versus the robust group, they're eating a lot of hard, rough, tough, fibrous foods. Like a good example, like a modern example, but imagine even way more than this. Like a modern example is like a jicama. It's like got a big husk, right? It's very fibrous. You have to get all of that off the outside of it, and then it's like the good part in the middle. So imagine a lot of foods like that, or even just you're just chewing. Like my advisor always says, imagine like a bipedal cow the robust group, they're just chewing, chewing, chewing all the time. So you can imagine if you're eating soft, ripe fruit versus if you're chewing all day long, your teeth, the mandible, the muscles for doing all of that chewing, massive difference, right? So this is what we basically see. So if you go to the next slide, you'll see the robust features in contrast, which I already kind of said right now. So you'll see the brain size is essentially the same. The molars and the premolars on the robust group are massive. It says huge premolars and molars, but look what it says about the incisors and canines. They're small. So while the gracile group, all of their teeth were all kind of like medium to large, in the robust group, the genus Paranthropus, the the front teeth are really small, but their back teeth are massive. So once again, a big difference in the dentition, hi baby, of what we see with those two groups. Are you feeling better? Come here. You want to say hi? Let's see. Oh my god, did you just fart on camera? You're hilarious. You want to say hi? Want to say hi for a second? I don't know if the camera picked up her fart. You want to leave right here? No? Okay, come here. There's room right there. There's room there. Yeah, go. What's that? Oh no, what's that? What are you eating? Oh, was that food? Oh, cool. Okay, there's food everywhere. I think Waffle just farted on camera. I'm recording right now. Oh, yeah, I'll take care of that in a second. Yeah, she did. Just a tiny, but yeah. I'll clean it up in a second. Okay, so I'm sorry. So like you can see here, those features of the robust group, and it's this massive muscle complex, right? So the muscles that are attaching to the mandible and that are attaching to the head for chewing are insanely big. So you've seen someone, like you can look in yourself, or definitely if you've seen, especially a male, because their muscles, like a human male, the muscles are going to be larger in this area. You see them chewing or talking, the muscles are moving right up here, even into their head a little bit, like up here a little bit. So imagine in humans, our muscles are really small, like male to female human, the males are larger, right? But humans, compared to a lot of the other like hominins or apes or whatever, ours are like tiny, teeny, tiny, right? And so these robust individuals, the genus Paranthropus, their muscles are insane. And so basically the whole face and head has to accommodate these giant muscles. And it's all because of the difference in the diet. So if you go to the next slide, you will see kind of that side by side between the gracile on the left and the robust on the right. So you see from the top down, there's that big space. You can see the holes on either side of the skull. Like if you had looked at a human skull from the top down, our top of our head's a bit bigger, so you'd have to kind of tilt the head side to side to see those little holes. Very small in a human, right? It's for this muscle here called the temporalis muscle. It comes up and attaches to your head and to your mandible, so it allows for chewing. That's the one you see up on the head when you know. But typically on a human, you see it kind of right about here. In the robust group, that muscle goes so far up to the top that you'll see on that kind of second comparison, the body has to create extra bone. At this area over here, we call it the sagittal crest. You see it's kind of like, looks like a little bony mohawk. Essentially, the body has to create more bone for that muscle to have something to attach to because it's run out of skull. And so you see that feature. And then that space behind the zygomatic, that little space, that hole, is for that because that muscle kind of sets against the skull behind like your zygomatic arch right here. Now in a human, that little hole behind this is really small because our muscle is small. But you'll see here from the top-down view on the robust group, the one on the right, on that first image comparison, that hole is pretty big, right? Because that muscle that sets in that hole, is very big. You see the sagittal crest, and then you see the third one down. You see just the difference in like the mandible size. Now you'll see the gracile group. They're not teeny tiny in their features. It's still all like a medium size, but the robust group is just even larger. So we're going to go through some of these species individually. Now, the book gives you more, but I'm only going to give you 3 Australopithecines and then 3 Paranthropines, just so we keep it a little easier. So you can see here on this image, the Smithsonian did these really, really great recreations of the hominin species. Oh, my hair now. And I have these throughout the PowerPoints. You can see, it's one thing when you're looking at that skull, and you're like, oh, I can see the differences. You can even imagine in your head, like, what it would look like with the soft tissue, but sometimes seeing like these really great ones that they've done is just amazing, especially as you go through and you see like, oh, early part of our lineage, you're like, I guess it kind of looks something like us, sort of. I can see how that's in our ancestry, to like getting more and more recent to modern like Homo sapiens, and it starts to become really clear. It's really cool. So the three we're going to talk about, probably two more so than the third, but the three for the genus Australopithecus, we're going to talk about Australopithecus anamensis, afarensis, and africanus. So you'll see on the next slide, anamensis, we're just going to briefly talk about this one. So now we're moving into this whole new genera, right? We talked about the early genera before. Now we have this genus, the Australopithecus, right? So the first species is Australopithecus anamensis. Once again, you can see this really great Smithsonian recreation, with all the soft tissue built on top of that skull. You can see some of the type specimens. We've got a tibia, a humerus, part of the mandible, looks like part of the maxilla, some other long bone fragments. And so, like I've mentioned before, you don't have to have like the full femur or the full skull to be able to tell if you're looking at a biped or not. You could even have fragments of the bones, and depending on if you're looking at the right fragment, you can tell if that individual is bipedal. And so now we have, clear evidence of this group being fully bipedal, without a doubt. And we have so many more fossil specimens for these species than we had for some of the early stuff. So there's like no doubt with a lot of the stuff. You can see here some of those, even getting specific with the features about like the tibial plateau, the tibia, like the thickness of the tibia. So even having a fragment of the tibia is going to be able to determine whether that individual is a bipedal or not, right? Now we're looking at the teeth getting a bit smaller, especially that canine. Remember I said for the canine, for our lineage, the canine does not seem to be related. We don't have that in terms of a sexual selection trait. So that gets pretty small pretty quickly in our lineage. Sorry, I keep shaking the table. And we have here a slightly divergent hallux. A hallux is a technical term for your big toe. And so remember, we talked about for bipedalism, all of our toes are in line with each other. We don't have an opposable digit on our feet like we have on our hands, right? All of the other primates have it on their hands and their feet, at least the ones that are currently existing now, right? We're not the only bipedal primate to have ever existed. Those in our lineage, obviously, and even some other ones in other lineages, but it's just a little more rare than when we see like quadrupedalism as an example. But you'll see all of those, they don't have a digit sticking out to the side on their feet the way we all have on our hands, right? So we're kind of the weird ones in our lineage that we don't have that and all the other primates do. And so, of course, there's going to be a period of time where ancestrally that toe is sticking out to the side to where it has to kind of come in line, and you'll see more and more efficient bipedalism as that transition happens, right? And so you see here slightly divergent big toe, essentially, for the Australopithecus, at least for anamensis, right? And, it's slightly divergent, maybe sticking out a little bit. This is part of that transitional process, right, of becoming more efficiently biped. Natural selection is probably bringing that toe in a little bit. It's not as if mom and dad are going to have a toe sticking out to the side and their kids don't, right? There's going to be a period of time for that to happen, right? But everything is indicating that they're fully bipedal. All still kind of short. We're short at this time still, but bipedal. And you can see here kind of where anamensis fits into that timeline. Next one, like I said, just talking about that one briefly, but moving on a little bit more detail with the next one, afarensis. So once again, this really great Smithsonian recreation of afarensis, and this famous fossil called Lucy. So you'll see where she was discovered in Ethiopia. That's where I told you guys I had gone to Ethiopia, and I think I mentioned this to you in one of the previous videos, but it's a big point of pride for them, the Ethiopians, that some of the early fossils of humanity have been discovered there. And when I worked at the museum, it's the National Museum, but everyone's like, oh, the Lucy Museum, right? Because that's where they have her fossils. So it was really cool to talk to a lot of the people there, either working at the museum or just people we met while we were there on that trip. That it's like a big point of pride, and a lot of the stores and restaurants will have Lucy in the name. It's kind of cool, right? So this was a famous specimen because it was one of the most, really up until that point, basically one of the most complete full body skeletons. So you can see about 40% complete. But when you think about it, if you have something on the left side or the right side, you can mirror it onto the other side, right? So you're like, oh, we only have the left humerus, but essentially you know what the right humerus would look like too. So having 40% is actually closer to having like 80%, right? And even with the skull, when you have fragments, we know how things work in terms of like the physics of mandibles and the attachments and stuff. So even when you have fragments, if you have the right type of fragment, you can still determine a lot of the other connecting features. So even if, let's say, you only had 50% of the skull, if it's the right 50%, you could maybe even really know closer to like 80% or something like that, right? It's going to be dependent on what the fragments are, where they're located, what the specimen is, and all that, right? But so a really fairly complete skeleton for this individual. There's also another famous site called Laetoli, and there's a famous specimen called the Laetoli footprints. I don't know why. I just noticed there's a big typo, and I've already uploaded the PowerPoint. It says footmints. I don't know why it says that. It's supposed to be footprints. So basically, there was, some what we're considering the afarensis. Individuals were walking through this area in like the mud, and so it's got like the impressions of their feet. So volcanic ash came and like basically fossilized those footprints. Be aware, I guess, of a lot of these like over romanticized stories, whether it's like this class, another class, whatever, life. All we know is that there were footprints. We know most likely 2 adults, 1 juvenile, but that's it. And they were bipedal. Like that's the cool part of the specimens. You're like, oh, now actually direct evidence of their footprint is even more amazing to have on top of having the bone evidence, right? So like bipedal at this point. The nice longitudinal arch, everything, 3 individual footprints. And I think the consensus is that it was most likely 2 adults and 1 juvenile. So great find, right? Important even just with that basic information. But like I said, be aware, sometimes like this story and others often will get like over romanticized of, oh, it's the evidence of like the first nuclear family. We don't know any of that. It could have been 3 females. It could have been 3 males. Like there's no way to know. They could have been unrelated. They could have been related. We have no idea. So be careful. I mean, this is true. I've said this before. This is true for this class, at another class, life in general. Always have a critical eye. That's always going to benefit you, to be able to ask like those deeper reasons, like, well, why is this happening? Who benefits from this? Well, is that really accurate, or is that just, supposition? Having a critical lens with everything is always going to benefit you. So in terms of like even this, discussion right now, it's like, well, it could have been people who were related, but it also could not. There's no evidence of that, right? So be aware when you'll hear, sometimes I've seen other instructors kind of take this and run with it a little bit, so just be careful with that. But we do know, amazingly, 3 individuals, their footprints, it's incredible. More evidence of bipedalism. Next slide, you will see that side-by-side comparison of Lucy and a modern Homo sapien. So like I mentioned, they're all really short at this time. Fully bipedal, as you'll see, so everything about the bone structure of the body is indicating fully a biped, but they're all still quite small. Now, there is no goal towards being tall, right? That's not a goal. Evolution has no goal, right? There's no goal towards being tall. But when we look at our lineage and we say, oh, we went from short to tall, that's kind of a cool thing. And we can say, oh, this is kind of when that happened, right? So short at this point, right? And you can see that next to that are the actual bones that were discovered for her. So you can see fragmented in terms of the skull, but some good pieces, big part of the mandible, and the body, a big portion of the pelvis, the femur, we've got the tibia, we've got part of the foot, we've got the arm bones, we've got the ribs and the sternum. Like there's so much that we have. And you'll see in that first image, in orange is what was the bones, right? And the rest is what we can fill in and be pretty confident, I'd say, about the majority of it. I think pretty. Next slide. What's here? More on afarensis. Just to kind of note on afarensis, the ancestral features versus the derived, or remember, derived evolutionarily means like new features. So obviously we're looking at some ancestral features, of course, things like there's a little bit more prognathism, right? We see prognathism reduce in our lineage kind of as the lineage continues. This is interesting. And I talked about this on a previous one. So we see with Lucy, or, Australopithecus afarensis, fully bipedal, right? Everything about their bodies indicating they're bipeds. However, some evidence in their arms and their hand indicative of them having a life in the trees. Now, like maybe being arboreal a little bit. Now, is this because they are still in the trees like at that time? And so they're fully bipeds on the ground, but when they're in the trees, they're still doing a little bit of this and a little bit of that? Or is it just a lingering ancestral feature? Like natural selection's not going to get rid of a feature if it's not really in the way. And being fully bipedal and having like finger bones that are a little longer or a little more curved isn't really getting in the way of anything, as far as we know, right? So natural selection's not really going to act on it because it's just kind of neutral at that point. So is it that Lucy and the others in her species were fully bipedal on the ground, but in the trees sometimes here and there, or were they just fully bipedal on the ground and they happened to have some features that were just like a remnant of the past, right? Hopefully that makes sense to you. But then the derived features, we got thick enamel, frame and magnum placement, indicative of being bipedal. The hind limbs, clearly biped. The pelvis biped, right? The angled femur or the valgus knee biped. So clearly fully bipedal. We talked about habitual bipeds and obligate bipeds before, remember? This is an obligate biped. They're so silly. She's farting. I don't know if you can hear her. Oh, she's so silly. Okay. Next slide. Oh, yes. So now moving into the third one of the Australopithecines. So this is Australopithecus africanus. I didn't name these. I'm sorry. They all have an A. Animensis, Afarensis, Africanus. It's like they transition or the names do. Sorry. You just have to find little ways to remember them. So for Africanus, you'll see here on this image a very, very famous paleoanthropological find. This is the Tong specimen, Taung. Sometimes it's referred to as the Tong baby or the Tong child, something like that, or just Tong. I usually just say just Tong. This is a very, very famous find. It's important for a number of reasons. So the first, and as you can kind of see in the image, it has an endocast. An endocast is like a fossilized brain. Basically, sediment gets into like the skull where the brain would have been and creates and forms in the shape of the brain. So you can end up seeing, even in the fossilized endocast, like the lobes, how big the lobes would have been, how small they would have been, maybe even some of the lines of like some of the vessels. This is incredible information to have, right? You're like, oh, this lobe was way more developed than this lobe, etc., right? Having that's really cool. Another thing, it's a juvenile. We have a lot of adults. We can say, oh, here are the features of the adults. We have all these adult specimens, but having a juvenile is super important. Number one, because you get to see like the life course of these individuals. Like this is what they look like as, young, then a little bit older into their juvenility, then as adults. It's important to see, especially for like some of the features that we see in them as adults. Like, oh, this feature is really prominent. Well, is that a feature that comes during like their form of puberty? Like they don't have it as a juvenile, but they have it as an adult? Or is it something that happens, when they're young? So like that's always interesting to be able to tell like the life history of these individuals. Now I've got another dog dreaming. I don't know if you can hear that. I don't know if it's picking it up. She's doing she's like barking in her sleep. Chasing something probably. It's like a lazy Sunday here, that's why. Okay. Oh yeah, so a juvenile, the endocast also was the very first Australopithecus to be discovered, right? So there's a lot. We have Australopithecus animensis, Afarensis, Africanus, right? We found different specimens along the way for all three, and some of the other ones that are mentioned in the book too. But Tong, this was the very first one discovered, the very first fossil evidence of a group we would later know as the Australopithecus. So that's important, and it was found in Africa, so like clear indication of African origins, the first one of its kind discovered. Juvenile, endocast, like a lot of reasons why this is a very famous and important find. Now, let's see if I get ahead of myself a little bit. Okay. I thought I went into it a little bit in this class. I guess not. Well, I'll just say in the lecture I go into it a bit more, but I'll just kind of say right now that the person who discovered this was named Raymond Dart. Well, here's the story. So Raymond Dart is working at he's in South Africa. He's working at the university there. And he's working like in the anatomy lab, and he's teaching and stuff. And one of his colleagues one day brings in like a box of some bones and is like, hey, like my buddy works down at the local rock quarry. They found a bunch of bones. That's probably like baboons and stuff. But I figured you would like to have these extra bones for like teaching your anatomy labs and stuff. And he's like, cool, awesome. So he gives him the box. And then so he starts to go through them, and he realizes right away he finds this in this box is this Tong specimen, and he realizes right away this is not a baboon. This is a biped, a slightly larger brained biped. And he was totally accurate. He's like, this is something in our lineage. Well, of course, as the story goes with so many of these similar stories, that those in the scientific community were like, no, that's not a whatever. It's not in our lineage. It's probably a baboon deformity, or they make up something, right? And so of course he ended up being correct. But remember, they had all these preconceived notions that all of the ancestry of who we are as humans was going to happen in Africa. I'm sorry, in Europe, right? Not in Africa. Also, they thought they would find, ape-like bodies with these big heads, and here he's like, oh, bipedalism first. The brain it's on its way to being a little bit bigger, but it's still kind of smallish. They're like, no, this doesn't fit with anything that we have preconceived in our minds that we're going to find. And so later he was vindicated, obviously. And his story's not even unique. This happens with a bunch of these early finds, right? But moving on to the next slide, you will see kind of that timeline visual of like Anamensis, Afarensis, Africanus. And now we can move on to the second. Oh wait, I'm sorry, I spoke too soon. The next slide, a little bit more info on Africanus. So here we have the Smithsonian recreation of like the adult version, right? And here you can see the skull of the adult. So if I were to show you that image and I said, hey, this is something in the human, lineage, you would say, oh, I can kind of see that. It's a little more ancestral looking, like it looks kind of a little more like ape-like humans are apes, right? But when we think of an ape, we think, oh, they're more hairy or something, right? But humans are apes. But when we look at that picture, it's like, oh, that probably is in our lineage. Maybe, I guess that kind of seems right. But obviously a little more ancestral. We can see, we're like, oh, it looks similar to us, but it looks a little different too. This is why it's kind of cool to see how they do these. More sites, like I said, you don't need to know the sites by name, but here you can see we're talking about like South Africa right now. And remember, for the Australopithecines on their skulls, we're not seeing any of that cresting. That's all what we're going to see in the other group, the robust group, Paranthropus, right? Also, Africanus has a very unique feature. Now, all of the species look unique, right? But in terms of the intro course, sometimes you're looking at all of these skulls, you're like, oh, they all look the same. How do I tell them apart? You're like, oh, I can tell the human or maybe the Neanderthal, but some of the other ones, they look really similar, right? And so that's true. Some of them, well, if they're closely related, you're going to see some similarities, right? But if you were to, let's say, take more courses in anthropology, you would, be able to pick them apart more easily. But I will say, even for this intro course, Africanus has a facial feature that is very unique to Africanus, and we don't see it with the other species. And you can see it in this image. It's something called anterior pillars. You'll see this on the skull there. On either side of the nose, there's like this ridge of bone going from like the alveolus of the maxilla and like on the edges of the nasal opening. It's this kind of raised ridge of bone. People have dedicated their entire academic careers, written theses, dissertations on what are the anterior pillars, what do they do, what are they functional for, are they functional for something, is it natural selection, is it genetic drift, is it, So, but when we see this feature, we know, oh, that is definitely Africanus, right? So when we're doing the exam and you're having to identify some of these different features or some of these different specimens, you're going to be able to look at, oh, anterior pillars, I see that feature, that's definitely an Africanus skull. And in the lab, when you see it visually, it's going to be more clear than just looking at this two-dimensional photo. Moving on to the next slide. So now we're going to go into the 3 different species within the genus Paranthropus. So we've got Paranthropus aethiopicus, Paranthropus robustus, and Paranthropus boisei. At least those 3 are different from the other ones that all started with A, right? So here we have Smithsonian recreation once again. I think this one is of robustus. But you can see here, different from the other ones, right? So right away, even before we talk about the features, you should be able to see just on the Smithsonian recreation, the face is a bit flatter. The area up here on the face, the cheekbones is a bit more prominent, right? We're going to talk about all of that. So here, the next slide. Once again, this was earlier in the PowerPoint, but now you have another side-by-side of the gracile features versus the robust features, and 2 of the Smithsonian recreations kind of showing the differences in what they look like. And remember, like it says here, the reason for the difference is the diet. Same brain size, neck down, basically the same height. It's only what's going on here that's different between the 2. So moving on to the first one, we have Paranthropus aethiopicus. This very famous specimen here, you can see it's kind of a darker gray. This is nicknamed the black skull because the sediment, basically where it was unearthed, it kind of dyed it over millions of years, kind of dyed it and stained the bone, so the bone color is a little darker. So it has this nickname, the black skull. No mandible for this one, but you can see based on like where the alveolus of the maxilla is and like over here where the temporalis is, that mandible would have been pretty substantial in size, right? You can also see with this one, that cheek area, the bony structure of the cheek is very, very prominent. You'll also see, which is very important, you're going to see for all three of these in the Paranthropus genus, that sagittal crest, that bony mohawk. Like I said, that is, the body creates that feature because the muscle here on the side of the head becomes so big that the skull has run out of room for it to have something to attach to, so the body has to create more bone in the middle so it has something to attach to. That's how massive this muscle is for them. You'll see here massive teeth, right? When we talk about like the back teeth, the crest is there for sure, and a feature called flaring zygomatics. So what I was talking about here, the zygomatics, so basically, we have this bone here, the zygomatic, and right behind it is where that muscle, the temporalis muscle is. That muscle becomes so large that not only does the body create extra bone up here, but this part of the face gets pushed forward. And so the zygomatic, instead of kind of being like this, it starts to go like this because that muscle is so big behind it. So that's what we call the flaring zygomatics. Next slide, another timeline showing this branching event. And we're pretty sure, like the image shows, that Africanus, that is where we start this branching event. And then we get the first, Paranthropus aethiopicus. The next slide, moving right into the next one, Paranthropus robustus. So here you can see that Smithsonian recreation again, showing the little bit of a flatter facial profile, but a really, really prominent in the cheek area. And the skull, it's fragmented in the back, so you could see the beginning of where that crest would have been, and just based on the shape of it, we know it would have been a pretty big crest. And once again, that muscle, that temporalis muscle, is so big for that. You can see even the face, even though this is kind of a fragmented skull, even the face is very flat. Basically what's going on, like I said, is that muscle is so big behind there that it's causing the zygomatic to flare out this way. It's basically causing the face to do what's called a dished face. So the face becomes like this shape. It kind of becomes like, hot, like kind of flared out this way towards like the front, like this. And so it's being really flat in the middle and then kind of really prominent on the sides, all because of their diet and this muscle complex being insanely big. So you can see this long bullet point list of the features I've already kind of talked about, right? So hyper robust, these flaring zygomatics, the cresting, the front teeth, very small, like really small, back teeth, massive, insane. In fact, the premolars are so big that they're called molarized premolars because they're just all their back teeth, all the chewing teeth. Remember, if you want to know what primate is eating, you have to look at the back teeth. They're all really, really, really big. And then you'll see the bottom bullet point. This is an important feature. It's called post-orbital constriction. Post-orbital constriction. Now, just by that name, hopefully you're thinking of something with the eye orbit, right? The orbit of the eye, post-orbital. Yes, so I think hopefully that's a perfect segue. It's not. Okay, it's coming up in a few Oh, wait, what? Oh, I guess I forgot to put that image in. I thought that the next slide had an image on it. That's fine, I can describe it. But the next slide does have the timeline again, showing, kind of adding in Aethiopicus and Robustus into that. And then the third one, the third species on the next slide, Paranthropus boisei. So basically, as we go through those three, Aethiopicus to Robustus to boisei, just imagine all of the features just getting bigger and then even bigger. The crest gets bigger. Zygomatics flare out more. Muscle behind, even bigger. Teeth, even bigger. So each one of those three is just basically the features getting so massive, right? You can see here, once again, Smithsonian recreation. You can see just the whole face is a giant cheek, right? That zygomatic is flared so out because that muscle behind it is so big. Basically a similar list in the bullet points from Robustus to boisei. But okay, like I was saying, I'll draw you a little picture of the post-orbital constriction. So if we're looking like top down at a human skull, it's going to look like like that, right? Looking top down, we're going to see that shape. If we tilted it from side to side, we might see a little bit of the zygomatic arch, you know, in that little tiny space behind it, because our temporalis muscle is kind of small. That's what it would look like in a Homo sapien. Now, for the robust group, though, what we're going to see is the shape of the head is completely shifted. So if you look top down, it actually looks something like this. And there's zygomatic, like in ours, is really tiny. Theirs is like this. It's insane, right? So this is all just open space right here. Open space to accommodate that giant muscle. So what it ends up doing is it causes this pinched in effect. Basically, like here are the eyes, right? Over here's like the back of the head. And so it's causing this pinched inness to right behind the eye. So there's this massive like physical separation between the brain and the eyes. Like if you looked at a Homo sapien skull, there's a very direct connection, but here there's this pinching off. And the shape of like the brain is way back here. There's this huge pinched off effect. So post-orbital behind the eyes constriction. So all to accommodate this particular diet, right? This diet of hard, rough, tough foods. Now, thinking about the difference in these diets, one being what we call a more generalized diet for the Australopithecines, and then for the Paranthropines being a more specialized diet. Pros and cons. Everyone wants to eat fresh, ripe fruit, so now you have a lot of competition. No one really wants to eat the leaves, so no competition, but maybe not the tastiest food. Like pros and cons to either strategy, right? So we see Paranthropus, that lineage eventually does die off. But if you look at the timeline, so move up one more slide, and you will see the timeline leading on to the humans, like before this branching event. That's still continuing, right? So I'm gonna talk about this like probably in the next PowerPoint. That the earliest in our genus, the genus Homo, are around. The early ones in our genus, the genus Homo, are existing at the same time as some of the Paranthropus, you know, species. So, like I've mentioned before, like now in 2025, we're the only currently like hominin species. But for a huge portion of our lineage, there was more than one, if not two or three different species within our lineage that are existing in similar parts of the world, and we have evidence that they interacted with each other. Like we had, up until recently, you know, we interacted with Neanderthals and Homo floresiensis, but as of like right now, we're the only ones. So it's kind of hard for us to imagine that if we were just out and about in the world and we saw another species that looks like us but is not us, you know. Let's see if I missed anything. Oh, and then the last slide, you'll see that comparison between Paranthropus boisei maxilla and then the human maxilla. You can see the front teeth are like around the same size, but the back teeth, look at that insane difference. Look at their molars. You could fit like 6 of our molars into their back molar, but our front teeth are basically the same size. That's insane, right? This is what we mean. You can even see those premolars. Giant, right? So it's because they're chewing all the time, causes all of those massive differences in the face, the mandible, and the skull, and top of the head, everything. Okay, so that's it for that one. A little bit longer, but we covered a lot in this one. So we'll see you guys on the next one.